And I'm gonna talk to you about the line drawings, following to Professor Han. Now there are some basic rules for the whole design. Uh, Basically, the fairing must be finished with a smooth soft surface, so no abrupt changes is allowed in curvature. And basically, the three major lines are should be adjusted until their intersections are in agreement. And always there is a mathematics of surface fairing, and there is nerves technique, non-uniform rational B-spline surface. This will be covered for following slides. In old days, the engineers used these tools to draw the ships, the extra, especially to draw the lines, the curves. They use these steel maiden tools to draw very beautiful lines, curves to their drawings. This is some simple process for drawing the curves. Actually, the right image explains the curvature of the curves. The perpendicular lines are representing uh, the radius of the curvature. So with controlling these straight lines, you can smooth the overall curve of the lines. So basically, you should eliminate the unwanted flex points, and as you design, some curvature discontinuities must be appeared in the composite curves. Okay, and this is the curve generation methods, and there is some many ways to about the curve definition. There is explicit method or the parametric representation methods. And the representation of the curves, you can use some spline algorithms such as Hermit or Bezier or B-splines, or you can use the nerves, non-uniform rational B-spline surfaces. It uses the B-spline, but it connects some the non-uniform surfaces for the hull. And to generate the curves, basically it uses the interpolation method to draw the smooth curves, or you can also use the approximation method. Okay, this is the Hermit spline. The Hermit spline's basic idea is using the 2 points and its incline, the slope, 2 points and 2 slopes. And if you choose the specific number, like n, and you can interpolate the lines between the 2 points. So as you can see in the right picture, there is 2 points P0 and P2, and the slope M0 and M2 is given, and you can interpolate the P1 and M1 using the Hermit spline. So I found some simple videos about this to understand the Hermit spline. If you cannot see the screen, let me know. So this user made a 2 point and 2 slopes. So changing the points or the slice, you can see that there is, you can change the curves with that. The second one is the Bezier spline. This method is quite similar to what you do as the basic interpolation. And this uses the sampling points, as you see, for the figures. If you only use the P0 and P1, it could be a simple, straightforward line, but using the many points, make a more complex curves like this. These are the moving image files to understanding. And I found some explanation video about this to understand the Bezier curve. Okay.
Hello everyone. Bezier curves are used to draw smooth curves that can be scaled indefinitely. I will be doing a lot of tutorials where I will be using them, so I thought maybe I should make a video explaining them, so you can have an idea of what it is all about. A Bezier curve is defined by a set of control points. For example, to draw a line segment we need 2 points, in this case P0 and P1. To get any point in this segment, we use a linear Bezier curve function, which is equivalent to a linear interpolation, with t varies from 0 to 1. This function simply means that the influence of each point depends on t. For t equal to 0, we will get P0. For t equal to 1, we will get P1. And for each value between 0 and 1, we will get a point along the line segment linking P0 and P1. Here is a visualization of how it works. Great, that was pretty simple. Now, what about drawing a curve? In this case, we need 3 points and use a quadratic Bezier curve. First, we need to do another linear interpolation between P1 and P2, and then interpolate between L0 and L1. This will give us Q0. If we trace the path of Q0, it will show a curve going from the first point to the last point. The first and the last control points are always the end points of the curve. This function can also be rewritten into this form. This is what is known as a quadratic Bezier curve. For a cubic Bezier curve, we need to add another control point, P3. We do a linear interpolation between P2 and P3. We call it L2. We do another interpolation between L1 and L2. And finally, we interpolate between Q0 and Q1. If we trace C0's path, it will look like this. We can rewrite the function into this form, and this is what is known as a cubic Bezier curve. So, after all, quadratic Bezier curve is just an interpolation between two linear interpolations, and the cubic Bezier curve is an interpolation between two quadratic curves. I hope this video helped you understand the basics of Bezier curves. Thanks for watching, and don't forget to leave your feedback and subscribe. See you next time.
Okay, this was the simple explanation about the Bezier curves. And the next one is basis spline. The basis functions are used to draw as the basis spline drawing. So the formula are like this. You can find in the Wikipedia or some other books. Maybe I think it is more easier to understand with the videos. The NURBS, the non-uniform rational B-spline surfaces, means some mass of the surfaces used to many B-spline curves. Okay.
In this lesson, we will learn about NURBS, objects, and modeling. NURBS stands for Non-Uniform Rational B-Splines. NURBS are useful for very smooth objects or when you need an exact surface. A NURBS object always has 4 sides and is made of mathematically created curves which are defined by control points. An individual control point does not show where that surface will be, but it is averaged with the surrounding points to create a curved surface. This means we cannot directly edit the surface. If we pull a control point, the surface will only move a little bit because we are averaging the change. To create complex objects using NURBS, we have to create many individual NURBS objects, often called patches. A common issue when working with NURBS is visible seams or breaks in the otherwise smooth surface between patches. But with care and correct workflows, we are able to hide the seams between patches so that this multi-patch object looks like a single surface. These difficulties mean that NURBS are rarely used in the computer graphics world, but it is often used in engineering and product design because of the very precise nature of NURBS. If you need to create a very smooth object or mathematically exact surface, try using NURBS.
Okay, this was simple explanation about the NURBS. So the basic idea is using many surfaces and stitch it together to construct the 3D objects. And finally, the computer-aided chip design. For these days, many the engineers do not use the papers, but most of them uses some computer programs to design the chips. So there are many conventional programs to design the hull, and it provides the parametric modeling of complex shapes. As we studied before, the hull shapes are quite complex, but using these kind of programs, you can design the complex shapes with the program. Quite simple. Like this image, you can change the little details using the program. So there are many programs such as Tribun and CATIA. This is famous for the 3D modeling, or the Easy Hull program. The last one is provides multiple formats to export to other programs. This is what I got today. Thank you for listening. If you have any questions, let me know. You can find some videos about the program running of the last part of the lecture. If you have interest, you can watch it from these links. Thank you.
Thank you for the nice videos and also explanation.